So we discussed the superposition and the Thevenin's theorem. But we missed out one theorem, which is the maximum power transfer theorem in AC circuits. So what power are we dealing with here? We are concerned with the maximum average power. Okay. So maximum average power transfer theorem. So let us consider a linear circuit which is delivering power to an impedance, load impedance ZL. Okay. So this is a linear active circuit. So that means it is delivering power. Okay. So this we are getting a Thevenin's equivalent. So we already know how to get the Thevenin's equivalent. This is VTH, ZTH, and here we have ZL, the load impedance. Now the Thevenin's impedance and the load impedance we will write in terms of their real and imaginary parts. So let ZL is equal to RL plus JXL, and even the Thevenin's impedance we will write as RTH plus JXTH. Then what will be the average power that is delivered? Average power delivered to load is given by the current square into only the resistor, right? What is the current? The current is the current flowing through the circuit. So this we can take as IL. Now IL, how you can write? Remember, these are all phasors. Okay, so IL bar, VTH bar. So IL you can write as VTH bar divided by ZTH plus ZL whole square into RL. So you can get mod VTH square, that means the magnitude of the voltage square, divided by root over RTH plus RL whole square plus XTH plus XL whole square into whole square, so you can remove this square root. Okay. So why we wrote like this? ZTH plus ZL is equal to RTH plus JXTH plus RL plus JXL. Okay. So what will be the magnitude of this now? This is going to be root over the real part square plus the imaginary part square. Okay. So that is why we wrote this expression into RL, which will be in the numerator. So this is what the average power. So this is the expression for the average power that is being delivered to the load. Now what we want? We want the maximum value of PL. Okay. At which load value we get maximum PL? At which ZL we get maximum value? So here you have two variables. What are the variables? RL and XL. So you have to differentiate with each of these. Differentiating with respect to RL and also differentiating with respect to the load reactance. So this is equal to 0. When you are differentiating with respect to RL, what will happen to XL? You have to consider XL as constant. Similarly, here you have to take the load resistance is equal to constant. Okay. So if you are doing this, then the final result I will write here, RL is equal to root over RTH square plus XTH plus XL whole square. Okay. So this is the result. Here what is the result you're going to get? XL is equal to minus XTH. So therefore, if you substitute XL is equal to minus XTH here, you're going to get, this will become 0. So RL will be equal to RTH. So the final impedance you're going to get ZL is equal to RTH minus JXTH. Okay. So this is nothing but the conjugate of the Thevenin's impedance. So this is the condition for maximum average power transfer. Condition for maximum average power transfer. So this is in fact something that you can guess also, right? So what will happen when ZL is equal to Thevenin conjugate? The equivalent impedance, that is ZL plus ZTH, that is the equivalent impedance, right? ZTH and ZL, they are in series. So now ZL is equal to ZTH conjugate plus ZTH. Then what will you get? Only a real value you are going to get. The imaginary part is going to get cancelled. Okay. So that means there is no reactance. So for purely resistive circuits, you are going to have the maximum power factor, right? Cos theta is going to be maximum for purely resistive circuits. Okay. So this is something that you can get from normal common sense as well. But this is the mathematical proof. So now we know the condition. Now what is the maximum value of the power, right? Therefore, PL max is now equal to mod VTH square divided by RTH plus RL whole square. So they are both equal. So you can write as 2 times RTH whole square plus XTH plus XL whole square is 0 into RTH. So what are you going to get? VTH square by 4RTH. So you can see that this is the same expression that we got in DC. Okay. So but remember, here we are taking the RMS values. Here VTH is RMS value. If you take the maximum value, then what will happen? You can write PL max is equal to VTH square divided by 8 RTH. Because here in place of the RMS value, if you write in terms of maximum value, what will it be? V maximum divided by root 2, but there is a square here. So V maximum square by 2 you will get. So here you are going to get 8 RTH. Okay. So this is when using maximum values, and this is when using the RMS value. Okay. So don't get confused. Now sometimes what happens is the load will be purely resistive. So in that case, what will be the condition? If load is purely resistive, this means that XL will be equal to 0. Okay, so then what is the only condition left out? We don't have to do the differentiation dou PL, dou X is equal to 0. We don't have to do this because there is no X at all here. Okay, so only the first condition we will need. What was the first condition that we derived? In such a case, we only differentiate PL with respect to R, which is equal to 0, RL. So here you are going to get RL is equal to root over RTH square plus XTH plus XL whole square. This is the same expression that we discussed previously as well. Since there is no XL here, we are simply going to get RTH plus XTH whole square, which is nothing but the magnitude of the Thevenin's impedance. So this is the condition if the load is purely resistive. This is the condition for maximum average power transfer. Okay.